So we're going to cover 11.2 chi-square test for homogeneity and dealing with independence as well. So we're going to go over these big ideas and we'll go through the check your understandings to make sure everybody's got a good understanding on what to do with this. So looking at this 11.2 part 1, so for a class project, Abby and Mia wanted to know if the gender of an interviewer could affect the responses to a survey question. The subjects in their experiment were 100 males from their school. Half of the males were randomly assigned to be asked, would you vote for a female president? By a female interviewer. The other half of males were asked the same question by a male interviewer. The table shows results. So we got a two-way table there set up for that. And it's wanting us to state the appropriate null and alternative hypotheses. So again, looking at our big ideas, our hypotheses, there is no difference in the variable distribution for whatever population is your null, and your alternative is there is a difference in the variable distribution for whatever population you're talking about. So looking at this, we should see that our null hypothesis should be there should be no difference in the distribution of responses to the question when asked by a male or a female, because that's the big key thing they're looking at here, whether or not a male interviewer or a female interviewer reflects on their decision. So with your null hypothesis would be there's no difference. Your alternative hypothesis is there is a difference in the distributions. So again, there is no difference in the distributions of response to the question when asked by a male or female is your null hypothesis, and your alternative is there is a difference in the distributions. Okay, so we've got the null and alternative hypothesis calculated here. So now we need to show the calculations for the expected counts in the male/yes cell, then provide a complete table of the expected counts. So with this, we're looking at for our expected counts, so our expected counts is the equation of the row total times the column total all over the table total. So we have to do that for each one of these. So the first one I want us to look at is the male/yes column. So with that, we're looking at male and yes, we're looking at this column right here, right? So male and yes is 30. But again, with that, we're looking at the totals. So it said the row total times the column total over the entire total of the whole setup, right? The entire count. So for our male/yes, we're simply going to take 50 for our column total times 69 for our row total, all divided by 100. And with that, we should come up with a 34.5. So that is for the male and yes. Okay, so now it's wanted to say a complete table of expected counts. So therefore, we have all of our expected counts. So let's just make a little table then. Or a box, probably a little bit easier, I should say. A little box set up here. Okay, so we know we got our yes, our no's, and then our maybes, and we have male and female. Well, we know the male and yes, we just calculated, is 34.5. And then we're going to look at females and yes, we used to be looking at dealing with a different color here. So we're looking at this column, so female, right? So we got 50. And then we still have 69 as well, and we still have over 100, okay? So therefore, that would get us the same setup there, 50 times 69 divided by 100. So this value should be 34.5 as well. Now let's look at dealing with our no. So the no, again, the only thing that's going to change here is instead of using our row total of 69, we use the row total of 11. So with this one, this is the value we're going to look at mainly for this. So for the no, let's say male and no, we would simply say we have 50 times 11 all divided by 100, and that should give us 5.5. Okay, and that would be the same for the female and no, because there's still 50 for our our column total, and then our row total is still going to be 11. So we should get 5.5. Now let's do the maybes. So in the maybes, the thing's going to change there is instead of 11, we're going to use 20 for that one. So we're going to use 20. So with that, if we do, let's say the maybes and yes, that would be 50 times 20 divided by 100. And that equals 10. All right, and that would be the same for the females as well, since we did the males and maybes. I'm sorry, not yes. I did maybes and I erase that. I apologize. Say maybes and male. Okay. So with that one, with maybes and male, we got 10, and maybes and females, we would have 10 as well, because both of those column totals are 50. So now we have all our expected counts. And part C here, it says calculate the value of the chi-square test statistic. So with this, it's wanting the long equation, right, for that setup, in which case we're using what we had in our other big ideas for 11.1. We went over that. So in 11.1, we looked at dealing with this equation right there to figure out our chi-square. So to do that, again, that is simply taking the sum of observed minus expected all squared over the expected. So to calculate that, we can simply go through the writing out of doing all this. Now, to write it out, you can do shorthand notation, and then we know that we got to actually put all these values in the calculator to figure that out. And to do that, again, let's deal with the first set of four. We had the male and yes, we had 30 count, and then our expected that we had right there was 34.5, and we'll square that, and we're going to divide by 34.5. And we're going to go through each one of these. We do the same thing for the females and yes, and then we do males and no and females and no, and males and maybe and females and maybe. And just for shorthand notation, I'll write all these out. Just going to do the last one here, which will do females and maybe. So we would have our observed, we showed was 8. Right there, we had 8 minus our expected of 10 squared all over 10. And the calculations I came up with, that was 4.25. So I got 4.25 for my chi-squared test statistic. Okay, so that's what we're looking at for dealing with 11.2 part 1. So let's go into 11.2 part 2. So with this one, it says for each of the following situations, decide what type of chi-square test is appropriate. So we'll go through and look at these and read through them and see what we got. So with this one, it says shopping at secondhand stores is becoming more popular and has even attracted the attention of business schools. A study of customers' attitudes towards secondhand stores interviewed separate random samples of shoppers at 2 secondhand stores of the same chain in different cities. The two-way table shows the breakdown of respondents by gender. So with these, we're going to have to look at our big ideas for this to look at. So we have set up here, we have for our chi-square goodness of fit test, we have one sample, one variable. For the homogeneity right here, we have two samples and one variable. And then for independence, we have it's a one sample and two variables. So we got to figure out how this fits, which one of these it is. If it's a goodness of fit, homogeneity or independence. Okay, so we're going to look at this and see what we have. So this first one, it says that they did a separate random sample of shoppers at 2 secondhand stores. Okay. So random samples at 2 secondhand stores. So for this one, we have two separate random samples. Okay. And let's see. And they're going to see the two-way table shows the breakdown response by gender. So as interviewer, so we're looking at one to see how this respondent's by gender. So we just have one variable here because we're wanting to see if the gender explains their decision, right? So with that one variable, simply dealing with the gender. So we have two samples, one variable. And if we look at our big ideas, goodness of fit is one sample, one variable, so it's not that one. But the homogeneity is two samples, one variable. So our chi-square test for that is what we're looking for. That's the type of chi-square test we're going to use. So our answer, you simply write out chi-squared for homogeneity. Okay. All right, so let's look at the second one. All right, so the general social survey asks a random sample of adults their opinion about whether astrology is very scientific, sort of scientific, or not at all scientific. Here is a two-way table of counts for people in the sample who had 3 levels of higher education. Okay, so let's see here. How many samples do we have? Well, it says we just asked a random sample of adults, okay? So therefore we have one random sample. All right, so now let's see how many variables we have. Well, with this, when we're looking at this, they're wondering if it's not scientific at all or very or sort of scientific. And then we're also looking at their degree field, right? So whether or not it's associate's, bachelor's, or master's. So we've got 2 variables depending upon their degree or their opinion. So we have 2 variables, okay, pertaining to their degree and the opinion they have. Okay, so now if we look at our big ideas, so we're looking at one sample and 2 variables. Well, for one sample and 2 variables, we're looking at our chi-square test for independence. All right, so we've got our chi-square for independence. Okay, so that's the answer for number 2. For number 3 here, it says casinos are required to verify that their games operate as advertised. American roulette wheels have 38 slots, 18 red, 18 black, and 2 green. In one casino, managers record data from a random sample of 200 spins of one of their American roulette wheels. The table displays the results. So it's on one wheel and one sample. Okay. So for this, right off the bat, I ran a sample of 200 spins. So we got one sample, as I said. Okay. And then it's looking for one variable, right? It's looking for the colors, right? So we're looking at here, the color. So we just have one variable as far as what color it lands on. So we just have one sample, one variable. Look at our big ideas. And this goes to the first one we have listed here. This is our chi-square for goodness of fit. This type of chi-square test we would use on that. So one sample, one variable is chi-square test for goodness of fit. All right, so that mainly goes over everything that we take away from the big ideas that covered for 11.2 here, dealing with your hypotheses, your expected count, as well as the degrees freedom. Definitely key to understand this as well. Looking at your rows minus 1 times the columns minus 1 is how it's calculated degrees freedom when you're looking at your chi-square test. Instead of just taking your sample size minus 1, as we've done in the rest of our degrees freedoms, dealing with means. However, on this one, degrees freedom, you're going to be taking your rows minus 1 and your columns minus 1 to get your degrees freedom when dealing with this. So this is a very important equation to take note of because it will come into play for sure. All right, so hopefully that helped explain things a little bit better and that you learned a little bit something today, and I'll see you next time.